So two theorems that follow from differentiability. Oops, there's the first one. We said that a function must be continuous in order to be differentiable. So if you have a function that you know is differentiable, you may assume that it's continuous. If I give you f prime, or you're able to find f prime, or there's a picture of f prime, you may assume that f was continuous, because we wouldn't have been able to find the derivative if it hadn't been. Second theorem we call the intermediate value theorem for derivatives. So all this means is that since f prime, the derivative, is another example of a function, so the way it's written on your paper, if f is a function that's differentiable, therefore it must be continuous, and it's differentiable on this interval a to b, then between a and b, f prime of x must take on every value between f prime of a and f prime of b. So this picture could help. If I happen to know there is a function f, and here at a, it had a slope of 1/2, so f prime of a is 1/2. And here at point b, where x equals b, it has a slope of 3, so f prime of b is 3. Then somewhere between a and b, this function must have a slope of anything between 1/2 and 3. So we have two examples here. This picture, probably, at least some of you, at least half of you saw this on your Chapter 2 test. I've been asked to name all of the x values at which f is not differentiable, and to justify my answer, referring, of course, to the definition of differentiability. So, two things I have to watch out for, just in that informal definition. My function is going to be not differentiable anywhere it's discontinuous, so everywhere I have a discontinuity, and it's going to be any place where it's not smooth, so a corner, a cusp, or a vertical tangent. So I'm going to write up an answer first here. All right, so this is what I've written as a beginning of an answer. I would say that f of x is not differentiable at x equals 0 or at x equals 2, because f of x is not continuous at x equals 0 or x equals 2. Good. So now you're wondering, this is 6, you didn't mention x equals -1. You're totally right. This function is not continuous at x equals -1. I didn't mention it as a place where the function is not differentiable, because when x equals -1, the function doesn't have any value. There's a vertical asymptote, which implies that there is no y value possible at all. So that means that x equals -1 was not part of the domain of the original function. So we wouldn't bother saying that the function isn't differentiable at x equals -1, because x equals -1 isn't even part of the domain. Now, so there's 3 places where this function is discontinuous. X equals 0 and x equals 2. So I say the function is not differentiable there, because the function is not continuous there. X equals -1, I left out of the list, because at x equals -1, because x equals -1 is not part of the domain of this function. So it's 3 places. I think there is one more place where this function is not differentiable. So I'm going to write it up, referring to the definition of differentiability. So this is that last point at x equals 1, there's a corner. So what my write-up would be, f of x is not differentiable at x equals 1, because the derivative from the left of 1 is not equal to the derivative from the right at x equals 1. So this is the formal definition. It's what you wrote onto your green paper. It's from the page before, and I've let c equal 1, because x equals 1 is the x value where this function is not differentiable. And if you want to understand what's going on, it's the slope of that little linear piece, so between 0 and 1, has a slope. It's going uphill, right? So the slope must be positive. The piece coming after, right after x equals 1, is going downhill, so its slope must be negative. So I know those two slopes can't be equal, and this is the formal write-up to say that the derivative from the left is not equal to the derivative from the right. Now we have one last example. Example 2, I have a piecewise function. F of x is x squared to the left of 3, and f of x is 6x minus 9 for x is 3 or greater. I want to know if f of x is continuous at x equals 3, and I want to know if it's differentiable. So first, we have to find out if f of x is continuous first, because if it's not continuous, then it won't be differentiable for sure. So how do I find out if a function is continuous? You thought I was going to stop asking you. No. A function is continuous at x equals 3 if the limit as x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right of f of x, which is all equal to f of 3. So I'm going to find those three values. So first, to find the actual function value, I use this piece down here because if I want to find f of 3, I need to find for which piece does the domain of 3, x equals 3 active. So I have the or equal to sign here. So I plugged in 3 to 6x minus 9, and I got 9. Now I'm going to find the limit as x approaches 3 from the left of f of x so the limit as x approaches 3 from the left of f of x. I'm going to find the limit as x approaches 3 from the right of f of x, and I'm just going to double check that they're both equal to 9. So when x is less than 3, those are for values of x that are less than 3 to the left of 3, I can compute the limit, and I get the limit as x approaches 3 from the left of f of x is x squared, so 3 squared is 9. I'm going to use the second piece, which is active for values of x that are to the right of 9. So I get the limit as x approaches 3 from the right of f of x equals 9 as well. I'm going to write up my first answer here to the question, is f of x continuous? So here I wrote up the first part of my answer. F of x is continuous at x equals 3 because the limit as x approaches 3 of f of x is equal to f of 3. Now I'm going to have to find the answer to my second part. Is f of x differentiable at x equals 3? So I'm going to use my new definition for section 3.2, which is when is a function differentiable? It's when the derivative from the left equals the derivative from the right. So watch my write-up. So I'm going to take the derivative from the left and double check that it's equal to the derivative from the right. That's what I'm hoping is going to happen. So from the left, I'm going to take the limit as x approaches 3 from the left of f of x minus f of 3 over x minus 3. And from the left, the function that's active is f of x equals x squared. So that's the limit as x approaches 3 from the left of x squared minus f of 3 would be 3 squared, which is 9, over x minus 3. Are you getting excited because you can factor? This is the limit as x approaches 3 from the left. That's x plus 3 times x minus 3 over x minus 3. Those are going to cancel. We're going to have the limit as x approaches 3 from the left of x plus 3. Now I don't have a divide by 0 problem anymore. I can simply plug this 3 in for x, and I get 6. Now from the other direction, I'm going to find the limit as x approaches 3 from the right of f of x minus f of 3 over x minus 3. And that's going to be the limit as x approaches 3 from the right of 6x minus 9 minus, what was f of 3? That's 9 over x minus 3. That's the limit as x approaches 3 from the right. That was a 3 up here, right? Of 6x minus 18 over x minus 3. But I can factor the numerator. That's the limit as x approaches 3 from the right of 6 times x minus 3 over x minus 3. These guys will cancel for me, and I have, again, 6. So I'll go back to the other slide for my write-up. So I would say that f of x is differentiable at x equals 3 because, essentially, the derivative from the left equaled the derivative from the right. So my write-up is because the limit as x approached 3 from the left of f of x minus f of 3 over x minus 3 was equal to the limit as x approached 3 from the right of f of x minus f of 3 over x minus 3.